Chapter 17. In chapter 16, we always had the acid plus water, which is the Ka, or the base plus water, which is the Kb. Both of these are mixtures, and what we do is we take the strongest acid and react it with water. In this case, the strongest acid is the acid, and the strongest base is water, actually. In this case, the strongest acid is water, but the strongest base is the base. And so in chapter 17, what we're going to be doing is we're looking at other mixtures. And for these other mixtures, we do the same thing. We take the strongest acid and combine that with the strongest base present. They don't have to be strong acids and strong bases, but just whatever is strongest. And so we'll have different mixtures. Let's take a look at some of the mixtures. And then just try to outline those. So the first one would be a mixture of strong acids, so a mixture of acids. And so we'll have acid A and acid B, etc. We have more acids in there. And so what you'll do is you'll just pick the strongest acid, whether it's A or B, and then react it with the strongest base present. The strongest base present is going to be water. And so this is just more Ka type stuff. We'll look at some examples of that. One example of that actually would be like if acid A and acid B are strong acids. Both strong acids. If those are strong acids, then we just combine the H plus. Combine total H plus, or hydronium, in solution. So a quick example of this is if you had, let's say, 1 molar HCl and 1 molar HNO3. The combined H plus from this would be 2 molar. So this would be 2 molar H plus or 2 molar hydronium. So you figure out how much H plus you get or hydronium you get from the HCl, how much from the HNO3, and just add them together for the strong acids. All right, if one is a strong, the other is weak. One strong, one weak. So let's say I had 1 molar HCl and 1 molar acetic acid, HC2H3O2. So in this particular case, because of the common ion effect, we might not have to worry about acetic acid contribution. So step 1 will be the HCl, Ka, which is very large. Step 2 may not be necessary for pH. Not necessary. At least in this particular example, it wouldn't be necessary because we'd end up with 1 molar H plus from step 1. And we end up with 1 molar hydronium, and we plug that in as a product here. There's so much product there, it's going to inhibit the forward reaction and make the contribution of H plus or hydronium from acetic acid negligible because of the common ion effect. Because of common ion effect, call it. The only time that we would worry about step 2 is if step 1 were very low concentration. Let's say I had 10 to the minus 7 molar HCl, then there's barely any HCl. It's almost like pure water. And so in that particular instance, the acetic acid would be significant. So only if HCl concentration were, less than let's say 10 to the minus 6 molar, like 10 to the minus 7, 10 to the minus 8, 10 to the minus 9 molar, we work it out. Now, this is about, we do the calculation. We have 2 weak acids. Let's say, I mean, we could have more, but let's say we have 2 weak acids. There are 2 ways we can handle it. One way is if the K's differ significantly, then we do it stepwise. If the K's are about the same, then we might have to do it simultaneously. Nearly the same. So if both have about the same contribution, then they're going to perturb one another. And so we'll have to do it. Now, stepwise, we're talking about the Ka's. And so we're still doing acid plus water. All these are Ka's. Because the strongest base in acid solution will be water. Yeah. All right. The same for bases, the same scenarios result. So if I had 2 strong bases, then what I do is I do the KDs and just total up the total hydroxide. If I had 1 strong base and 1 weak base, then the main contributor of hydroxide would be the strong base, and the weak base would be a negligible contributor because of the common ion effect. If I have 2 weak bases, then the same type of situation occurs here. This type of situation is very similar to what we see for, let's say, phosphoric acid. Phosphoric acid is triprotic acid, and you do multiple steps here. The only difference is we might have 2 monoprotic acids rather than 1 polyprotic acid. Let me fill it in. Okay, now these are mixtures of acids and mixtures of bases in water. What if we had a mixture of acid and base? And so let's look at some mixtures of acids and bases. Acid and base mixtures. The acid and base mixtures that we're going to see are going to be strong acid, strong base. Strong acid plus strong base. We call this a acid-base titration. This would be like HCl and sodium hydroxide. And we call that a titration. It doesn't have to be a titration, but in this chapter we classify it as a titration. Then we have weak acid plus weak base, or not weak base, so strong base. This again would be a titration. Then we have a strong acid plus weak base. Of titration. And so a weak acid, strong base, the typical example here would be something like acetic acid, which is weak acid, plus a strong base, sodium hydroxide. And what we're going to form is sodium acetate in water. A strong acid and this weak base would be like HCl and ammonia, aqueous ammonia. example of that. The products of this would be ammonium and chlorine. Then we're going to have a weak acid and a weak base. A weak acid, weak base mixture is what we call a buffer. If the weak acid and weak base are unrelated, that is, an example of that would be like ammonia and acetic acid. Then we have to do this one simultaneous. That is Kb for ammonia, Ka for acetic acid, and Kw for water. Etc. Is normally ammonia plus acetic acid, that would form ammonium acetate. Well, what's ammonium acetate going to do to pH? When we try to calculate the pH, we need either hydronium or hydroxide as a product. And so how do we do that? Well, we want to do, K of the reaction. This is going to give us K of the reaction. This is called a neutralization reaction. The problem is it doesn't completely neutralize. When we have a strong species, strong, then what we'll see is it reacts completely. But when we have weak species only, then they only partially react. And so it just partially neutralizes. If they're related, what I mean by related is if they're conjugates, then the math is much easier. If they're conjugates, an example would be like ammonia and ammonium. And so the base is ammonia, the acid is ammonium, or acetic acid reacting with acetate. So the acid would be acetic acid, the base would be acetate. Then this is much easier. These are what we call Henderson-Hasselbalch buffers. Henderson-Hasselbalch buffers. And for Henderson-Hasselbalch buffers, we could just do a normal ice table. Ice with Ka or Kb. It's an easy way to handle this. But this one is simplified into the Henderson-Hasselbalch equation. So we don't even have to do an ice table. So simplified to the HH equation, which stands for Henderson-Hasselbalch equation. Ice table is not necessary. And so it just makes it a little bit easier for the calculations. Since we don't have to do it like that. So when they're, when they're unrelated and related, this is difficult. This is pretty straightforward. And so most of the buffer problems we're going to do are going to be like this. We don't have to do too much. But the reason it's called a buffer is because of this. The buffers are they're a stable mixture of acid and base. If I have something like HCl and NaOH, this is not a stable mixture of acid and base. They're going to react. And if they neutralize one another, they'll form sodium chloride, a neutral salt. If we have excess acid, then we're going to have excess acid left over. It's just going to be acid. Or if we have excess base, will be excess base left over, and it'll just be basic. And so it's either going to be neutral, acidic, or basic, depending on the stoichiometry. The same thing here. If we have a weak acid and a strong base, they're going to react with one another. And here, they're going to react with one another. In other words, we come up with this thing, which is strong bases, or strong acids and bases. Just strong, we'll just say reacts to completion. So the way we tackle these problems here is the strong reacts to completion, determine what's left over. Determine what is left over. For the Henderson-Hasselbalch, we just looked at the ratio. And we can easily figure that out. Okay, so let's take a look at some simple terms. I have to post this chapter 17 homework. I forgot to do that. But we'll take a look at some of the homework. So we finished chapter 16 last week. So officially we're supposed to have the exam this week, like on Thursday. How does that sound?
Not super great, given the amount of homework.
Yeah, given the amount of homework, I know it's a long homework assignment. Maybe too long. So I could do it either on Thursday or Tuesday next week. That helps. Tuesday. Okay. We could do it Tuesday. Normally, when I do the homework myself, I actually go through every single problem. I think I mentioned that earlier, when I went to UCLA, the guy next to me ended up getting a tough score the physical chemistry exam. So I started talking to him because I bombed the first test in physical chemistry. This is my first quarter there at UCLA. I thought, oh man, already underwater. And so I figured, he told me what he did, and he went through every single homework problem. I thought, how could you go through every single homework problem? Well, at UCLA, they give the complete solutions manual. They don't deal with the partial. In at least all the classes I took that had the solutions manual available, it was the complete. Because their thinking goes like this, if it's homework related, that's not a challenge problem. Challenge problem would be a step beyond the homework, and so they didn't care if you had the complete solutions manual because they'll just make a problem harder than anything in the homework. And so anyway, that's how you could do it, because you don't actually do it. You just read the problem and read the answer quickly, and then you kind of get the whole picture, the whole forest of problems. And then you go through that multiple times, and then you can kind of figure it out. But, I often do that just to see. Some of these you think, the Chem 1A style, they make it more challenging, but they do Chem 1A type calculations, which you're trying to avoid on my test. Since Chem 1A is the biggest class. And so some of those I don't pay much attention to, other ones I do pay attention to. But, okay, so this is some acetate, propanoic acid here, weak acid, 10-5. And HI. So this is a strong acid, weak acid. Now, if they're only asking for pH, and this is fairly concentrated, strong acid, 0.0892, even though this is more concentrated, because of the common ion effect, it's going to be a minimal contributor. And so what you do is you could do this calculation here and see that this is going to be a minimal contributor. What I do is I just read the answer and see what happened there. It's not just doing the problem. You could do the problem, and then what you have to do is after you do the problem, you kind of have to, dig deeper into it. Like, what was the take-home point to that problem? Was there a take-home point to that problem? Or how does this problem fit into the general forest of problems that you might see out there? And then, you get more out of it. It's just, if you just do, okay, I did the calculation, that was it, that's usually, you could do more, or you could get more out of it. Let's see what happens here. So we'll do this one. This is a standard strong acid, weak acid mixture. So strong acid, weak acid mixture. I told you that the strong acid is going to dominate the pH, and the weak acid should be a negligible contributor. But in this particular problem, they want the inventory. So if they want the inventory, then we are going to have to do the whole thing. And so this follows the same kind of procedures as chapter 16. What we do is we do step 1. Step 1 is the biggest K, or the strongest acid with the strongest base. So the biggest K is going to be, well, we only have acids here, so the base is water. And so the biggest K is going to be HI. And so that's going to be 0.0892. And so we're going to do Ka for the HI. HI is a very strong acid. And the Ka for this, we should have memorized for all the strong acids, is very large. Okay, so HI, and that means your book skips this step here, but I do it because it's the pattern. Let's see. And so acid plus water gives hydronium and iodide. So this is going to be 0.0892 molar initial, 0 and 0. And then the change is going to be minus X plus X plus X. And so at equilibrium, we're going to get 0.0892 minus X molar, X molar, and X molar. And so K for this, actually, if the K is very large, then we know what the change is going to be. What does it change? It's got to be 100%. And so X in this case is going to be 0.0892, which is going to be 0. This is equal to plus 0.0892. This is plus 0.0892. So this is the reason your book skips this step, because if I have 0.0892 molar HI, then I have 0.0892 molar hydronium. It's a given. So you could skip this step here too. but I do it. Okay, now we go to propionic acid. Prop means 3 carbons. This is a 3 carbon carboxylic acid. So that will be step 2. The next biggest K will be CH3, CH2, COOH plus water. This is going to produce hydronium plus propanoate. Propanoate is going to be CH3, CH2, COO minus. It's like the acetic acid produces acetate. So it produces the 8 ion. All right, now the concentration for this is even higher, 0.275 molar, but the problem is that we're going to have quite a bit of hydronium here at the start. So we'll carry this down here to step 2, and that's it. We don't carry anything else. So the change here is going to be minus X plus X and plus X, but I don't know what that is. Since I already have quite a bit of hydronium in here to begin with, you know, this is almost 10 to the minus 1. You know, almost 10 to the minus 1 means a pH of 1. So is that weak acid really going to make any difference in this case? I'm not going to think so, but let's check it out. So Ka for the weak acid here is 1.3 times 10 to the minus 5, which is equal to, you know, the hydronium times the propanoate divided by the propanoic acid. Why they call it propionic acid. Well, propionic acid. Propionic acid, this would be propanoic acid. And so this is going to be x squared. Oh, not x squared. It's going to be 0.0892 plus x times x over 0.275 minus x. What we're going to do is we're just going to use the simplifying assumption. And so this is going to simplify to 0.0892 plus x is just 0.0892. X is just x. And then 0.275 minus x, which is 0.275. And so what does that come out to? So 1.3 times 10 minus 5 will just be 0.013 times 0.275 divided by 0.0892. So I get an x equal to 0.04008. Okay, which one is going to be the bigger percent change? The numerator here or the denominator? 0.0892 plus x or 0.275 minus x? Which one's going to be the bigger percent change? The numerator. Actually, so it's going to be, the percent change is going to be 0.00004 thousand divided by the initial, which is going to be 0.0892 times 100%. Actually, my calculator rounded this to, and there's more digits, it's 4,007. Depends on what orientation I have. Portrait versus landscape. I'm just going to carry the digits in my calculator here. Divided by 0.0892 times 100. And I get, what did you get? I got And so if I'm interested in the pH, I wouldn't have done step 2, because if I'm interested in the pH, this is not really going to change the pH much. So if I go from 0.0892 to 0.08924, what would the pH have changed? So if I stopped at step 1, the pH I would have calculated is based on this. So the pH would be the negative log of 0.0892. So it would be 0.0892 log 1.049. If I stopped here, I would have gotten a pH of 1.0496, etc. If I go here and do step 2, what would I have gotten as my pH? And so I would have done the log of 0.08924. And I would have gotten a pH of 1.0494. Actually, it did change. You see, it did change. But the problem is how many sig figs are we allowed? We're allowed 2 sig figs. And so I'd have to round this. This would round to 1.05. That would be 2 sig figs. This would round to 1.05. And so with the number of sig figs that we're allowed and the uncertainty, it doesn't add it's not a significant contributor. A significant contributor would have significantly changed the pH with step 2, but it didn't. And so if I'm interested in pH, I wouldn't have done step 2, even though I had a higher concentration in weak acid. But they're not asking for the pH. They're asking for the hydronium here. Okay, so if I did the hydronium, would it have made a difference going on to step 2? If I stopped at step 1, I'm allowed 2 sig figs, so this would be 0.089. If I go on to step 2, I'm allowed 2 sig figs, which would be 0.089. And so still, if we're just the hydronium and the pH, I wouldn't have done step 2. However, they want hydroxide. If they want hydroxide, then I have to go beyond step 2. I have to go to step 3. Right? And let's do that. Let's just make it a longer problem. So we'll do it. Your book doesn't actually do the ice table for step 3. This is what your book does. Your book assumes that step 3 will contribute to negligible amounts of hydronium, which it does. And therefore, they're just going to calculate the hydroxide, assuming that this is the final concentration of hydronium. Well, we'll just do it. I mean, they take a shortcut, but the thing is, before you do the shortcuts, you should learn the long way and then take the shortcut after you're comfortable with it. And so we'll just do it the long way, which is step 3 is H2O plus H2O liquid. This is going to give us hydronium and hydroxide. And so initial hydronium, we're going to carry down from step 2 to step 3. So 0.08924. And hydroxide is 0. So the change here is going to be plus X plus X. And so we'll get 0.08924 plus X molar and X molar. Now K for this, which is KW, is 1.0 times 10 to the negative 14, which everybody should memorize at 25 degrees C. It's useful. There's going to be 0.08924 plus X times X. Here we'll just use the SA, assume that this concentration doesn't change much. And so we get 0.08924 times X, and then calculate X. So your book will go straight to this equation here after doing the SA. So let's skip all these steps, go here, and then calculate the hydroxide, which is X. So we'll go 1 times 10 to the negative 14, 1 times 10 to the negative 14, divided by 0.08924. what we get is x is equal to 1.12, I'll just carry that, times 10 to the negative 13, 1.12057 times 10 to the negative 13. Okay, now when we look at this, this is almost 10 to the minus 1, 10 to the minus 2. We'll take this as a 10 to the minus 2. And so the change is 10 to the minus 13. And the initial is a 10 to the minus 1, 10 to the minus 2. I'll call it 10 to the minus 2 to give it that extra margin. So this is going to be 10 to the minus 13% change. 10 to the minus 13% change is negligible. And so in this case, it didn't change the hydronium. I mean, we'd have to write 12 zeros, which we're not going to do in this case because you can get the point. And then this one will be 1.12 times 10 to the negative 13. Now, one thing we'd like to do is, even though, let's say we're interested in the hydronium, we'll calculate everything just to make sure I didn't make any errors in this. And so over here, this is 275 minus quadruple 04. And so this will be 0.2746. And this will be quadruple 0.408 more. So what we're going to do is we'll just double check our K values to make sure the K values are okay. Which I forgot that earlier. Because I should have checked this before going on to step 3, because if I did make a mistake in step 2, I don't want to have to correct both step 2 and step 3, so I forgot to do this. But it's handy to do because it just makes the point quadruple 0.4008 times 0.08924 divided by 0.2746. 1.30 times 10 to the minus 5. 1.3025 times 10 to the minus 5. And so that checks out. Okay, let me check the K value here to see if this one checks out also. So I'll take 1.12 times 10 to the minus 13. I'm not going to carry up a lot of extra digits because it should be pretty good, considering that percent change, minuscule. Times 0.08924. And I get 9.9948 times 15, which is going to be about 1.0 times 10 to the minus 14. Okay. So what they want is they want the hydronium. Well, since we did all the steps, this is the hydronium. It's step 1, step 2, and step 3 combined. Then the hydroxide is just strictly from step 3, 1.12 times 10 to the minus 13 more. And then there's an error here. There should be a negative sign on the last oxygen. This is CH3CO2, CH2CO minus, which would be propanoate. Propanoate stops in step 2 here. Or actually, this would be the molarity of that. And then they want the iodide. The iodide comes from step 1 here. And again, it's here. This would be the iodide.
How do you know which one to do for step 1, step 2?
You pick the one with the biggest K. not the biggest concentration, the biggest K. The biggest concentration was this is mixed up, these. Okay, this is number 2 is a weak base and weak acid. This is a weak acid, weak base mixture. A weak acid, weak base mixture we call a buffer. So let's take a look at that. And is this unrelated or related? Related. They're conjugates to one another. And so what we could do is we could use the Henderson-Hasselbalch equation. And so let's take a look at the Henderson-Hasselbalch equation here. We don't have to. We can just treat this as normal ice. So 0.164 molar ammonia and 0.102 molar ammonia. So we have the excess of ammonia, but how's that going to impact it? So what we do in mixtures is we take the strongest acid, which would be ammonium, chloride's neutral, and the strongest base, which would be ammonia. And so what do we form? Ammonium plus ammonia. We're going to form ammonia plus ammonium. So what does that do for us? Nothing, basically. So then we look for the next strongest, base of the next strongest acid. Now, what we could do is, okay, if that doesn't do anything, we'll take ammonia and water. Or we can take ammonia and water. Or do we have to take both? Okay, so this is a dead end here. And so what we're going to do then is we'll look at ammonia and the next strongest base. The next strongest base will be water. And if we do that, we're going to form hydronium and ammonia. And so we could look at the acid and the water here. This would be Ka. And or Kb, because we have ammonia present too. And so if we have ammonia present, we'll take ammonia and water, and we're going to form ammonium and hydroxide. Yeah. Now, which one should we do first? The Ka or the Kb? Whichever is bigger? Yeah, usually whichever is bigger. That's what we do first. But when we have a weak acid, weak base, we're often interested in what the pH is. If we're interested in what the pH is, then we want to know how much hydronium. Now, the situation with this is we don't want to do both. We do either Ka or Kb. Do either Ka or Kb. Usually we pick the bigger one. Normally we choose the bigger one.
By bigger, you mean more concentrated?
No. By bigger, I mean bigger K. The Ka for this one's 5.6 times 10 to the minus 10. The Kb for this one is 1.8 times 10 to the minus 5. So we should pick Kb. In this case, Kb is the one we should pick. because it's bigger. But do you notice something about these two equilibria? What are these equilibria describing? Okay, this equilibrium is describing the equilibrium between ammonium and ammonia in water in terms of pH, hydronium. What is this one describing? This one is describing the equilibrium between ammonia and ammonium in water in terms of, yeah, hydroxide or POH. And so these are the same equilibrium. Only one is talking about the pH, the other is talking about the POH. Well, normally we're interested in the pH. And so although we should do this one because it's bigger, we're going to do this one because it saves us one extra calculation. But conceptually, there's a tricky point to this. And I'll talk about that when we do it. But these are the same equilibrium. So what we do here is we just start off initial. Now, they tell us the solution is both this, so we don't have to do what's called a solution dilution. Usually when we mix two solutions together, we have to do solution dilution. In this case, we don't because it's already here. 0.164 molar ammonium and this one, 0.102 molar ammonium. So I skipped this step. Ammonium chloride goes to ammonium and chloride. That's K is very large for that. And so there's a step here before. That's it. And then we'll start off with zero hydronium. Likewise, if you wanted to do Kb, we could have done Kb. The ammonia would be 0.164 molar, and the ammonium would be 0.102 molar, and the hydroxide would be 0. And so if we calculate the ice table for Kb here, we end up with the hydroxide, get the POH, figure out the pH. If we do the ice table for the Ka, we'll get the hydronium at equilibrium, and then we'll get the pH. And so both of these will give us exactly the same pH, pretty much. Aside from round. Okay, so let's go ahead and do this. Here's going to be minus x, plus x, plus x. Over here, we're going to get 0.102 minus x, x molar, and 0.164 plus x. Now, when we look at this, we have a lot of product here. And so x should be negligible. And so what we're going to get is Ka is going to equal x times 0.164. I'm going to skip the writing the expression out. Divided by 0.102 minus x. And then we'll go ahead and go straight to the simplifying assumption. So this is going to be x times 0.164 divided by 0.102. And then calculate what our x value is. All right, 5.6 times 10 to the minus 10. Right. What does our chart say? 5.7 times 10 to the minus 10. 5.7, 5.6. I forgot what it says. I'll just use this since I already wrote it down. Times 0.102 divided by 0.64. Our x comes out to 3.48 times 10 to the minus 10. And so our initial is about 10 to the minus 1, roughly. And so the percent is going to be about 10 to the minus 10 over 10 to the minus 1 times 10 squared. which is 10 to the 9 minus 9, 10 to the minus 7%. 10 to the minus 7%, which is good. Okay, so this is going to be 3.4. What are they asking for here? No, asking for change, right? This is 3.48 times 10 to the minus 10. Well, I'm going to just take the log of this. I didn't write all the digits, there are more. Yeah, I get a pH of 9.458. I'm allowed 2 sig figs for this here, so we'll just call this 9.5. Do the pH, 9.46, sorry, 9.46. Would be 2 sig figs. All right, let's do this over here. So this would be minus x plus x plus x. And so at equilibrium, I'm going to have 0.164 minus x, 0.102 plus x, and x over here. Let's put this into kb. This is going to be 0.102 plus x times x divided by 0.164 minus x. We'll use a simplifying assumption again here. So we'll get 0.102 over 0.164 x. Then solve for x. So I'm going to have 1.8 times 10 to the minus 5. Times 0.164 divided by 0.102. And so again, x equals 0.00028942, quadruple 0, 2894, etc. Which one's going to be the bigger percent change? Well, x over 102 versus x over 164, x over 102. And so we'll do the percent change, which will be x over 102 times 100. And so I'll take this number divided by 0.102 times 100. And I get 0.028%. And so that's minuscule as well. Not as small as that one, but plenty big enough for this. And so what does that give me? Well, that gives me a hydroxide ion concentration of quadruple 0, 2894. More. So let's go ahead and take the log of that. 0.02894 log. And then add that at 14. Do that again. 0.02894 log. So I get a pOH of 1.538, which gives me a pH of, let's just screw this up, 12.461. So, I did something wrong here because these should come out the same.
Your pOH is wrong.
My pOH is wrong? What did you get for your pOH?
4.535.
Alright, let's see. pOH. Yeah, I have trouble with this calculator consistently. So, 0.002.894 log. Yeah, it shouldn't be 2. Yeah, 4.53885. pOH is 4.5385, which means the pH is equal to you know, because of rounding differences, I have a pH of 9.46 here, a pH of 9.46. This is the same, they're describing this. So if I did this, it would be like going in circles here. You know, if you did both the Ka and the Kb, you'd be going in circles. Get the same answer. Let's look at the other concentrations. Are we going to get the same concentrations? Yeah, in fact, we are going to get the same concentration. This is going to be about 0.102. This is going to be about 0.164. Because 10 to the minus 10 is not going to make much of an impact. Going over here, this is going to be about, this is going to be about 0.164. And this is going to be about 0.102. All right, so calculate the hydroxide, ammonium, chloride, and hydronium. Now, I told you that there's one trick to doing this. You know, we usually pick the bigger one. We pick the bigger one, the bigger K. We should have done this using the KB. The reason we should have done this because it's the bigger one, and two, because this is a basic solution. Basic solution, you look at the pH is almost 9.5, which means it's on the base side of the thing, which means the hydroxide ion concentration is dominant. When I look at the hydroxide ion concentration here, should I do Kw? Do you think Kw will make any impact on this? No, because Kw will be like 10, you know, this is common ion effect, so we're looking at 10 minus 8, 10 minus 9, 10 minus 10. That would be, you know, anywhere from 7 to, 10 zeros here, let's say. It's actually going to be quite small, because the pH is kind of high. And so, hydroxide from water should be negligible. And so I wouldn't do Kw. Now, if I didn't do Kb here, and I looked at this, and I got a hydronium of 10 to the minus 10. If I had a hydronium of 10 to the minus 10, then you go, wait, will hydronium from water be significant? And you'd say yes, because this is 10 to the minus 10, it's minuscule. But the problem is it's not, because this is a base solution, and the base solution, hydroxide, is dominant here. And then when we look at this, water is barely going to lead to any additional hydroxide. Now, that's because of common ion effect. So this is still going to be minuscule in terms of hydronium. So the problem with this is this. If you're thinking about doing Kw, you might be tempted to do it incorrectly, because a base solution is based on hydroxide. An acid, if this were an acid solution and my hydroxide were even smaller than this, then yes, I would worry about Kw here. Does that make sense?
We know it's a base solution because the Kb is bigger than
Yes,
Ka.
right.
The only way we can tell that.
Yeah. The Kb is bigger than Ka, so we're going to produce more hydroxide than hydronium. And so it's going to be a base. Even if the concentrations were disparate, this concentration we have, not only do we have more base, it is based on the solution, but let's flip it. Let's say we had less base. I'd still expect it to be base dominant because the Kp is big. Is there another question?
So at the beginning, we made it pretty clear that we use either Ka or Kb based on the bigger one, but then I remember you said something like, well, so, and then it ended up doing Ka and Kb and Ka first.
Okay. I said you could do either Ka or Kb, but we should do Kb.
Yeah.
We could do Ka, we'll get the same answer. So if we get the same answer using Ka, then the preference is to use Ka because it saves us one calculation. The one calculation it saves us is having to convert POH into pH, because we get the pH directly. And so we save a little bit of time.
But the problem is now, would that just be more practice for calculating pH, but the problem is
The problem doesn't ask us for pH, but it could have. And the other situation is this. The other situation is the problem with, since we're doing this stepwise, the problem of KW, do we or do we not consider KW? For acid solutions, we look at the hydronium contributors. And so if this is the total hydronium, then we got to worry about KW. But this is not an acid solution because base dominates. We already saw that base is going to dominate because Kb is bigger than Ka. If base dominates, then we're over here, and we shouldn't be asking, is water going to be a significant contributor to hydronium? It's a base solution. We've got to be asking, is water going to be a significant contributor to hydroxide? Okay, so what we're going to do from now on is we're going to use Kb. We're not going to use Kb. We're going to use Ka for all scenarios. From now on, we'll just use Ka. But, whether we factor in Kw or not depends on what the solution is. So we gotta worry about that.
Do we also have to do step 3 since it's asking for hydronium as well and OH?
Okay, do we have to do step 3? If you say Kw is going to be negligible contributor to hydroxide, then the hydroxide is not going to change. If the hydroxide doesn't change, the hydronium doesn't change. And so this is our step 3. And so what we did was we said that the hydroxide is just going to stay here, and therefore we calculated pOH. Otherwise, I would have done step 3 and then calculated my pOH. Yeah. And so we already eliminated step 3 at this stage. We said, okay, the hydroxide stops here. Step 3 is not going to contribute much more additional hydroxide. We get the pOH based on that, and that's going to give us the pH. If this is the pH, then we can get the hydronium ion concentration. The hydronium ion concentration, if we did Kb, is going to equal 10 to the minus pH molar. And so we just plug that in here and then calculate it. But since I already have it, it's going to come out to 3.48 times 10 minus 10. That's going to come out to 3.48 times 10 to the minus 10. So if you look at the hydroxide is 2.8 times 10 to the minus 5. And the hydronium is 3.48 times 10 minus 10. Hydroxide dominates this solution in space. All right, so a couple of things to note here. One, the common ion effect usually means that the change is negligible. And so one thing we notice in this type of problem is that the initial and the final concentration is the same, about the same. Not exactly the same, but about the same. Initial and final are approximately equal concentration here. And the same thing here. And the same thing here. And the same thing here. And that's because the change was not significant because of the common ion effect. Change was not significant because of the common ion effect. So let's take a look at the Ka equation in more detail. So although we should have done the Kb, we're going to do the Ka just to save us a tiny bit of time. Kw is not going to be significant, usually, in these types of problems. Yeah. All right, so this is what we're going to do. We're going to say that Ka is equal to the hydronium ion concentration at equilibrium times the ammonia concentration at equilibrium divided by the ammonium concentration at equilibrium. Okay, if we look at the initial concentration, it's 0.102, but rather than calling it 0.102, I'm going to just call it initial. So this is going to be equal to the ammonia concentration initial minus X times, oops, I forgot the hydronium concentration, like that. It's going to equal the hydronium ion concentration times the ammonia concentration, initial, minus X, divided by, okay, the ammonium concentration will be, that equilibrium would be the ammonium concentration initial, this will be plus X, right? This will be minus X here. Okay, I think I got it right now. And so this is ammonia initial plus X gives us ammonia at equilibrium, and then ammonium initial minus X gives us ammonium at equilibrium. So this is what we have. Now let's go ahead and use the SA. If we use the simplifying assumption, which should work as long as we have enough concentrations, but we'll get the hydronium concentration at equilibrium is equal to the ammonia concentration initial divided by the ammonium concentration initial. Now, what we're going to do is we're going to take the log of both sides. And so what we're going to do, we're going to take the negative log of both sides. And so we'll take the negative log of both sides. So we'll get the negative log of Ka is equal to the negative log of, I'm going to split it up like this. I'm going to put it as the negative log of hydronium at equilibrium times, and I'm going to put this separately, the ammonia initial over the ammonium initial. So using the property of logs, I'll just add these here. And so you know what the negative log of Ka is called? The pKa. So the negative log of Ka is the pKa. And the negative log of hydronium, what's that called? Negative log of hydronium. Not the pKb, but the power of the hydronium, pH. So actually, I better write it down. Yeah. So I'm going to get the negative log of hydronium minus the negative log of ammonia initial over ammonium initial. Okay with that so far? So this is going to equal to pH minus the log of ammonia initial over the ammonium initial. So I'm going to add negative log of ammonia over ammonium to both sides. And so I'm going to get the pH is equal to the pKa of ammonium, in this case, plus the log of ammonia initial over ammonium initial. This is called the Henderson-Hasselbalch equation, the HH equation. The advantage of the HH equation is we just put in the initial values. If we just put in the initial values, we don't have to do the ice table. We don't have to do the ice table because the common ion effect is going to tell us. As long as the simplifying assumption holds true, we don't have to do the ice table for this. We just plug in the initial values here, and the pKa is just the negative log of the Ka.
Was all the work kind of like your proof and then that kind of is like the equation that you squared? Is that like the universal equation that you squared?
Yeah, what I did was I did it, all that work was unnecessary for this particular problem, if I'm only interested in the pH. If I'm only interested in the pH, unfortunately, I'm not only interested in the pH of this, but oftentimes I get a solution like this, what is the pH? And so if question number 2 only asks me for the pH, if number 2 only asks for the pH, only asks for pH, then it's easy. I don't have to set up an ice table, no ice table. The pH is equal to the pKa. pKa is negative log 1.8 times 10 to the minus 5, which is 4.74, plus the log of the ammonia initial over the ammonium initial. So that's going to be the log of ammonia initial, 0.164. And the ammonium initial is 0.102. And so that's 474 plus, okay, what's the log of that? So 0.164, 0.164 divided by 0.12. 0.26. When did I get this pH earlier?
9.46. Sorry, 4.14. 9.45.
The pOH was,
pH?
or the pH was, this is actually
The pH is 9.46.
9.46. Oops, I did a mistake, sorry. I did a mistake here because the pKa is the native log of the ammonium. Ka for ammonium. I actually put the Kb in there. What was the Ka for ammonium? The native log of 5. I wrote 5.6 times 10 to the minus 10. The chart up there has 5.7 times 10 to the minus 10. But I didn't want to change it. And since our chart, I'm pretty sure it's 5.6 times 10 minus 10. I believe it. No, 9.25. 2518. So 9.2518. And 0.26. Let's see what the calculation is. 9.25 plus 0.286. 9.4578, which gives us the pH of 9.46. Is that what we got earlier?
Yeah.
That's what we got earlier. And earlier we had to do the ice table and all that stuff. In this case, we don't. We just use the Henderson-Hasselbalch equation and get the answer here. Unfortunately, they asked us for more than the pH, and so we had to do it. And therefore, we could get these numbers from there. The chloride, I skipped that step, but it would be 0.102 molar chloride. That would have been the soluble salts have a very large K. All right. So let's do a generic. There's a KB version of the Henderson-Hasselbalch and a Ka version of the Henderson-Hasselbalch. So let's look at the Ka HH equation really quick. And we take a generic acid, HA plus H2O liquid. Are we out? Just hydronium plus A minus. Initial change equilibrium. So we'll have the HA initial minus X gives us the HA initial minus X at equilibrium. This will be the 0 molar here. This will be the A minus initial. This will be plus X plus X. Then we get X and then A minus plus X. Okay, this one we're going to just call the hydronium at equilibrium. And so the Ka is going to equal the hydronium at equilibrium times the A minus initial plus X divided by the HA initial minus X. Okay, the only thing is we have to make sure the simplifying assumption works. If the SA is valid, then the Henderson-Hasselbalch is valid because this simplifies it for hydronium times the A minus initial divided by the HA initial. So if the simplifying assumption works, then we get the pH is equal to pKa of HA plus the log of A minus, which is the base, to HA ratio. There's a KB version of the Henderson-Hasselbalch too. Usually we just use the KE version of the Henderson-Hasselbalch. The KB version will give us the pOH instead. Now, usually the KB version, normally the bases are negative or neutral. And so the KB version is B or A minus. These are the same. So normally when people do the KB version, they say base plus water gives us HB plus OH minus. Like that. Or A minus plus water gives us HA plus OH minus. These are two ways of representing those. And so I'll just use the second way just as parallel. And so we'll have A minus initial, HA initial, and 0 for hydroxide initial. The change here is going to be minus X plus X plus X. So we get A minus initial minus X, HA plus X, HA initial plus X, and then X. X is going to be the hydroxide concentration at equilibrium. And so we get the KB is equal to the HA initial plus X times the hydroxide at equilibrium divided by the A minus initial minus X. If the SA works, then HA initial plus X is just the HA initial times the OH minus equilibrium. And this would be A minus initial if the simplifying assumption works. And then we take the negative log both sides, and we have the pOH is equal to the pKb, in this case, pKb, plus the log of the acid over base ratio. The initial acid over initial base ratio. And so this is the pOH version, or the KB based version of the Henderson-Hasselbalch. Only reason I'm bringing, I never use this. I never use this, but there's a homework problem that asks something like this. And so, don't bother with the pOH version of this.
You said this is like a lot easier because you don't have to do the ice table, but don't you have to do the ice table to see if the SA passes?
Okay, the essay is always going to work. The essay is always going to work unless your initial concentrations are too low. What do I mean by too low? And so the essay will always work because we're dealing with weak acids and weak bases. So SA is valid unless your initial concentrations are too low. So what do I mean by too low? What I mean by too low is think about this. If I keep diluting this with more and more water, let's say this is Windex or something. I keep diluting this with more and more water, eventually what's the pH going to be? 7, because it's going to be like pure water. And so what happens here is when these are too low, then the pH approaches 7. And so what is too low? Well, if you're trying to, this is what we call a buffer solution. And the thing is, the cost of the buffer solution depends on the cost of the materials you use for it. And so you could have a highly concentrated buffer solution with a pH, let's say 9.6, which we had there. The pH just depends on the ratio. And so as long as we have the same ratio, we should get the same pH or pOH. But it doesn't depend on the absolute magnitude of the concentration. And so if we made a buffer, let's say that has 10 molar, let's say here, if we made a buffer that has 16.4 molar ammonia and 10.2 molar ammonia, that's a lot of material. That would be an expensive buffer, right? And so that would be a good buffer because it has lots of acid and it has base in it. But we can get the same pH by making this, let's make it this quadruple 102 and quadruple 164. That would be an extremely dilute buffer, but it should have the same pH. If I try to extend that further and further out and make this more and more dilute, let's say I make it like 10 to the minus 10 molar on both sides, then there's barely any acid and base there, and this pH should approach 7. Okay, so as long as I have a reasonable concentration of initial, then the assay works because of the common ion effect. Yeah?
Is that just for weak acid and base?
Yes, it only works for weak acid, weak base that are conjugates of each other. You can't use this for any acid, any base. They have to be conjugate pairs. And they have to have a concentration that's not too ridiculously low. I mean, if you see a concentration that's ridiculously low, you've got to use the ice table in that case to prove that the assay works.
So you do conjugates that are like base?
If you have a strong acid and a weak base, conjugate, it doesn't work. It has to be weak and weak. We'll look at the examples of this next time. All right, here. And then what's tomorrow's lab?
We're not in the lab for the school.
I got it. What is it? The syllabus.
Qualitative analysis for
Qualitative analysis, day 1. Okay. Well, we're going to still continue that. But weighing the crystals doesn't take much time. So we're going to start a new lab tomorrow, the qualitative analysis. I'll post that lab today on Canvas, and I'll talk about setting up the notebook for that particular lab. But tomorrow I'll probably talk mostly about it at the beginning. We'll set up the notebook together tomorrow in class. Yeah.
In the our normal lab.
Yeah. So we'll be in the normal lab room tomorrow.